Okay, so Bronsted and Lowry, they had a slightly different view than Arrhenius did. They had a different definition on what they classified acids and bases to be. And so we saw in the last video, Arrhenius had a view of acids always starting with H plus, and bases always ending in OH, and they always made salt and water when you mix them together. And we saw above that it's not quite that way. We can see that H plus actually has to exist as hydronium in water. So let's take a look at a different chemical that Bronsted and Lowry might have studied, but their definition was a little more, well, a lot more different, I guess, in terms of what an acid was. An acid was a proton donor. So that is, it was able to give a proton to something else, and a base was a proton acceptor. So it was able to take a proton from another chemical. So let's take a look at ammonia, NH3, and let's think about if we put that into water. Now, what's interesting about ammonia is ammonia actually is a base. It does turn litmus paper blue. If you were crazy enough to drink it, it would probably taste bitter, although I've never actually tried that. But it does not have any hydroxide. So Arrhenius, looking at this wouldn't quite fit his definition of a base. Now, ammonia, if you look at the Lewis diagram for this, Lewis dot diagram, we have these lone pair of electrons up on top. And so if we put that next to water, what actually happens is the attraction for these electrons is strong enough that it actually is able to pull the hydrogen off of the water molecule. And so what that winds up giving us is NH4 now, because we stick an extra H onto there. And because it's a positive charge, we wind up getting NH4 plus, which is the ammonium ion. And we know from last chapter, ammonium is soluble with pretty much everything that I could think of. And what would the other chemical be now that would get formed here? Well, if you took an H off of water, that would leave you with just the OH part of it. And so your product now would also contain the hydroxide ion. And that's probably what a lot of people would associate as being basic, because they think of hydroxides as being basic. And so I guess in some ways it's kind of like Arrhenius, you're getting hydroxides, but looking at NH3 by itself, it's definitely not looking like a base. So let's think of that as the base. It's accepting a proton from the water, which that actually would make water a proton donor. So under this definition, I guess water is an acid. Say what? So that's strange. So water is not actually acidic. Water is a neutral compound, but in this context, it's actually acting as a Bronsted-Lowry acid. It's donating a proton to the base. Now, if the reaction was to go backwards, because you can see this is an equilibrium reaction, I want you to think about which chemical on the product side is acting as an acid, and which one's acting as a base. Well, the NH4 plus turns into NH3, so that would be losing a proton. So this compound here would be acting as an acid in the reverse direction, and the base would be the hydroxide. So that's that. Now let's take a look at a different reaction, just sort of use this concept here. So we'll write out a pretty obvious acid, something like HF, hydrofluoric acid, plus water, forming into. Now in this situation here, obviously hydrofluoric acid is going to be the acid. And what it's going to do is it's going to give its proton to water, which means water would be a proton acceptor, so it's actually acting as a base. And I want you to think about what would form now. Maybe pause the video, take a guess, see what you think. Well, if HF loses a proton to the water, it's going to turn into fluoride ion. and the water is going to turn into, that's right, H3O plus hydronium. So on the far side we have fluoride, which if it went backwards would take a proton, turning into HF, so it's acting as a base on that side. And the hydronium would be giving its proton to F minus, so it's going to act as an acid. So that's definitely strange stuff. Okay, so depending on the type of acid you have, the acids can sometimes donate more than one proton, and so they have different names. So we have what's called monoprotic, diprotic, and polyprotic. And so protic usually refers to the number of protons that can be transferred. So an example of a monoprotic acid would be something like above, HF, or we saw earlier hydrochloric acid. So those are all monoprotic, one H to give. A diprotic acid would be something like scribble that out, sorry, I've lost my eraser here. H2SO4 would be diprotic. And you can think of polyprotic being more than one proton, but maybe something like phosphoric acid. That would definitely be a polyprotic acid. And we saw depending on the acid, you can give up more than one H and get maybe more waters forming in that process. And another term we use in this chapter here is the word amphiprotic. Now, I always like to think of amphibians here. Not that I like amphibians; they're kind of gross actually. But amphibians are cool in that they can live on the land or the water. And so frogs, for example, they're able to breathe in the water, and they're also able to breathe on land. So amphiprotic means it has the ability to act as a bronchodilatary acid or a bronchodilatary base. Now, if we look at the above example, we can see water in the first example where it's reacting with ammonia. It's acting as an acid. And in the second example, when it reacts with hydrofluoric acid, it acts as a base. So it takes protons, accepts protons, or can give up protons depending on the situation. So water in this context would be classified as an amphiprotic compound. So H2O is an amphiprotic compound. So if it has the ability to take protons and also accept protons, then it's classified as being amphiprotic. Now, you might think about why a compound would be amphiprotic, what makes it amphiprotic, and we'll get into that in our next video. But for now, if a compound has the ability to give protons or take protons, it's classified as being amphiprotic. And then we've got above that monoprotic, diprotic, and triprotic. So where else do we got here? Yeah, so I'm going to stop the video here and then assign some questions below. So you'll see in the homework section, it'll say something like practice questions numbered 1. And that's going to relate to these videos. So good luck with that.